We're now going to consider what happens if we add some free charge into our polarized dielectric. So if we have some free volume charge, rho sub v, in addition to our bound volume charge or our polarization volume charge, then we'll have some total charge density, rho sub t, which is equal to the sum of the two. So we have our free volume charge plus our bound volume charge, rho sub pv. And for Maxwell's first equation, we know that that volume charge is going to be equal to del dot epsilon naught times E. Okay, and so now we can sort of play some games here, and we're going to get an updated, what we're working toward sort of at the end here is an updated definition of our electric flux density, and we're going to relate that to our electric field. So we can say that, rearranging here, that our rho sub v, our free volume charge density, is then equal to del dot epsilon naught E, and we've moved our rho sub pv to the other side, so we have minus rho sub pv, our bound volume charge density. Well, if we recall from the previous video, in our boxed equations, we had an expression for our polarization in terms of that bound volume charge density. And so what we can do is we can rearrange this, and using our properties of our dot product, we have that this can be equal to del dot, and then the quantity of epsilon naught times our electric field plus our polarization P. And so I'll just mention really quickly, when I first introduced our polarization P in the previous video, I did not have it as a vector quantity, and that was an oversight on my part. That should have been a vector quantity P. So at any rate, we now have this, and if we compare to sort of our initial form of that Maxwell's first equation, we know that that has to be equal to del dot d. So comparing that then, we see that our d has to be equal to what's here in the parentheses. So we can now say that our d is equal to epsilon naught E plus polarization P. And so again, remember, this is where we've added free charge into our polarized dielectric material. And so basically what this is just a more general form than what we had worked with in the previous unit. So more general form for our electric flux density. And so previously we had just assumed that our polarization was equal to 0 because we just had d equals epsilon naught E. So from this then, we can see that the net effect of this dielectric on our electric field is to increase that electric flux density. So net effect of our dielectric material on our electric field is to increase our electric flux density D inside the dielectric by an amount equal to the polarization. And so basically we're just saying we initially had this, and now we're adding this P. So that's what our dielectric provides for us. For some dielectrics, that polarization is proportional to the applied electric field. So for some dielectrics, and so for most useful ones at least, our P polarization is proportional to our applied electric field E. And so the equation that relates those two then is P, our polarization, is equal to our chi E epsilon naught E, where this chi E is our electric susceptibility. So electric susceptibility of the material. And essentially what that's doing is it's just measuring the dielectric sensitivity to the electric field. And so this is a dimensionless thing because of course we can sort of relate our units for our electric field and polarization and our epsilon naught, of course. So let me just write explicitly that this is dimensionless.